Dear colleagues, we're glad to be present in another ICDSST conference to present you our work on how we can formulate the problem of detection of changes, drifts, in the evolution of political events. Let us start this presentation with the basic data element that we need, a political event. There are various frameworks that dictate how an event can be codified and get registered once it is broadcasted by a news agency. The common elements that are being registered are the involved actors, the type of the event, and the corresponding date. I chose an example of an event that happened back in 1982, but unfortunately it is still relevant. You can see the original text that was broadcasted and how this is codified through the Cameo framework in the table at the left. Listening to and recording political events with a systematic approach and structured event data is a challenge that is being pursued since the 60s. But nowadays, especially after the G-Delta initiative supported by Google, political event databases are copious and are putting forward data-based approaches to analyze interactions at a macro level. Collection of political events is now easy. The challenge has shifted to the analysis side. This work makes one step further towards the process-oriented analysis of political events. In particular, the new research question is if we can detect changes, drifts, in evidenced interactions between actors that have the shape of unusual behaviors and stand out from the others. There are at least three reasons why such a question would add value to existing workers. First, anticipating the changes enables early warnings, and consequently, it timely leads to adaptive measures. Then, even if we assume a purely postmortem historical analysis, the drifts detection is both a requisite and a driver to relate drifts to causes, hence to perform inferential research. And third, in a domain where subjectivity and aesthetics can dominate the practices and the decisions, the availability of a tool to respond to such a question can contribute and give rise to evidence-based confirmations. There are 6 stepping stones in the proposed approach. Let us present each of them along with a working example that we have devised based on a real case study. So the first step is about transforming the coding of the political events, Cameo coding for instance, into a format that is enabled for process mining. In previous works we have proposed several transformation templates. In this work we exemplify the template that uses the pair of the two actors, the source actor and the target actor, as the case ID, and we keep the concepts of the event and the date intact. This way, a trace of a case indicates the evolution of the interactions between two countries. By applying ordinary process mining techniques on these traces, as we have demonstrated in previous works, we are able to discover the evolution of the interactions as a process map, which provides a straightforward visualization of how political events among countries unfold. So the next step is to identify higher order rules. The rationale behind looking for higher order rules is that we should not expect the next move to depend only on the last event that has occurred, but that the previous events are influencing the next event's occurrences as well. See, for example, a typical first-order network. It attaches branches to an activity without considering the previous moves, which is not accurate. Should we consider the previous moves, the resulting higher-order network becomes far more informative. So in this example, if I'm hosting a visit after a consult activity, chances are that I will make a pessimistic comment. While if I'm hosting a visit after a yield activity, probably I will express intent to negotiate. This distinction is not visible in first-order network. So what we actually do is checking if, while being in an activity, the distribution of the next moves changes, if we account for the previous moves or if we don't. If the distribution changes, we replace the activity in the network with a new composite activity of higher order. We do that by calculating the statistical distance or divergence via the Kullback-Leibler divergence with this formula, but other options could be possible too. To explain the next steps of the approach, we shall present the proof of concept that we have devised. We created an artificial event log by simulating a business process. So during the simulation, we artificially injected some changes. So in specific, there was an initial period when the execution was normal, meaning that the branching conditions in all gateways were balanced. Then we made a sudden change to one gateway and changed the 50-50% probability distribution to 90% and 10%. And after some time, we reversed those probabilities to 10% and 90%. And then we made a second order dependency to appear by modifying the branching probabilities of another gateway. And finally, we made an additional second order dependency to appear. So we simulated 200 cases for each scenario. Although we simulated each scenario for 200 cases, we split the windows, the time windows per 100 cases. This way, we ended up with 10 time windows, 9 window changes, 4 of them containing drifts, containing changes, and 5 not. Then, for every time window, we discovered the corresponding process maps. Once as first order networks, the baseline approach, and once as higher order networks after having applied our approach. So the next step was to compare the sequential graphs and calculate the pairwise distances. We used the discrete spectral distance, which is defined as the Euclidean distance between the spectra of the adjacency matrices. Nevertheless, other network distances can be calculated without any loss of generality, of course. So this matrix shows the distance between time windows before and after the log replacements. We want the white columns to contain low values and gray columns to include large distances, large numbers. So the results suggest that when higher order dynamics are incorporated into the event log, it is easier to detect drifts. But the advantage is not clear enough. So in particular, both options, both the higher order network and the normal network, avoided a reversal. That is, the distance is always greater in gray columns than in white. For gray columns, that is the actual drifts, higher order network is calculating larger distances, okay? Hence making the drifts more identifiable. Especially for the second order dynamics here and here, there is a clear superiority of higher order network. So for the white columns, that is the fake drifts that are attributed to randomness, sometimes higher order network is performing better, like here, and sometimes not, like here. It's worth pointing out that even when higher order network is not winning, it is very close to the performance, like here, while this is not the case for the option without the higher order network, like here. So, concluding, additional tests are required to validate any results. This is, of course, work in progress, but we are conducting additional experiments, and we hope that in short time we will be able to present you a more accomplished version. Thank you for attending the presentation. I wish you to enjoy the conference, and I will be very glad to answer your questions.